Students, hi, this is Mr. Bob. In this video, we're going to talk about Newton's law of universal gravitation. So you have two essential questions there. What does the equation for Newton's law of universal gravitation suggest? And the second one is, how does the universal law of gravitation connect to our study of circular motion? So keep those in mind as you go through the notes and make sure you've answered them or been able to give a good answer for them by the end of the notes. First, a quick story. So I don't know if you realized it, but the other day I accidentally sprayed deodorant in my mouth. Now when I talk, I have this weird accent. I'm sure you'd be roaring in laughter if you heard this in class. Okay, let's jump right into it. By now you should also have read the excerpt from the Bill Bryson book about Newton and the conversation with Sir Edmund Halley and kind of how he came up with this universal law of gravitation and just kind of the quirkiness of Newton and his sort of character. So just to recap what was talked about in that book or in the excerpt is in the late 1600s, Newton published this manual called Principia, which people have said is basically one of the greatest, most amazing feats any human has ever accomplished. But part of the Principia talked about this gravitational force between 2 point masses, mass 1 and mass 2. And Newton talked about how they were directly proportional to their product and inversely proportional to the square of their separation. Well, what does that mean in equation form? It means this. So if you want to figure out the force between two things with mass, any two things anywhere in the universe, no matter how big or small, all you need to do is take the mass of one, multiply it by the mass of the other, and divide it by the distance squared from their centers. Throw in a gravitational constant, kind of, this is like a proportionality constant if you want to think of it that way, and boom, you have the force that each body exerts on the other. Notice the size of the gravitational constant is listed there, 6.67 times 10 to the negative 11th Newtons meter squared per kilogram squared. So a couple of points I want you to remember about this law that sometimes tend to trip students up. Remember that the R that is mentioned is the separation distance between the center of the masses. And this is even true for something as big as a planet or a star, because those have a pretty big radius, but we assume that they're uniformly dense, which is a pretty good assumption. And so we can actually say that this law applies. The distance between them is not to the surface of each object, but to the center of mass. And lo and behold, if that's the case, we can draw a free body diagram in this situation. If I have mass 1 on the left and mass 2 on the right, then the force that 1 feels because of 2 is to the right. And similarly, the force that mass 2 feels from mass 1 has the same size arrow, but it's pointed in the opposite direction. And I do want to take a second to note that Newton's third law is obeyed here, right? If an object A or an object 1 exerts a force on object 2, then simultaneously that object 2 exerts an equal and opposite force on the first object. So it kind of all matches. Like I said, the radius of each mass does not matter because the Newton's law of universal gravitation is calculated from the center of mass to the center of mass. And notice this, again, this holds true for any two objects in the universe, including something as big as our moon, which revolves around our Earth. So how does this connect to our study of centripetal motion? Well, if you notice there, the moon is moving in a pretty circular orbit. We're going to assume it's circular for our purposes in this unit. So if the moon is undergoing uniform circular motion, then there must be a force exerted on the moon towards the center of that motion. Well, what is supplying that force that causes it to keep moving towards the center in a circle? In this case, it is the gravitational force. So when we're talking about the orbits of planets, moons, satellites, things like that, the gravitational force is the centripetal force, okay? And so if you think about it, they kind of add another idea here. Up until now, most often in our scenarios we've been looking at, it's been a tension force or a friction force, or in some cases, a normal force that is directed towards the center. But now in certain cases, the gravitational force is that centripetal force, and which is causing the acceleration which is directed towards the center. So if we look at the Earth, and I want to introduce this concept of a gravitational field. We're going to talk more about fields in general this spring. But if we were to draw what's called a gravitational field about the Earth, notice what I'm drawing here is lines that show the direction. So if an object was here, right, it would feel a force downward because of the gravitational field of the Earth. And similarly, an object here that I'm just kind of drawing these red dots. Notice if we put an object, a test object, so to speak, in this field or in this space, notice that it feels a force, and we can draw lines that show the direction that the force is directed. And those lines represent, in effect, how the Earth has warped the space around it, right? So if it's warped the space or changed the characteristic of the space around it, we can say that there's a field that's a kind of imbued in the whole area around the Earth. And we call it a gravitational field. Later on this spring, we're going to talk about electric fields, which occur when charged objects occupy a certain spot in space. The area around those electrical charges also is warped with something called an electric field. So if you notice from far away, the gravitational field of the Earth is not uniform in the sense that, like, an object right here is going to feel a smaller force than, say, an object that's closer right here, right? Because the distance and separation is a lot less. If I get closer, though, notice what happens to these lines. What starts happening to these lines? They start kind of getting grouped together. And if I get really close, right? If I get like just above the city line here, notice the lines that were kind of curved are pretty much looking straight. And again, I just want to point out here, the key idea in this slide is that when we get really close to the surface of the Earth, this field becomes what's called uniform, meaning it has a uniform strength. Okay, so notice over here, we can clearly say an object up here has going to feel a different force than an object here, a different gravitational force. An object here versus an object, say here, it's going to feel pretty much the same gravitational force because the separation distance is pretty much the same, as you can see, represented by those lines. Okay, so this is the point of the slide, to just kind of show you that at a localized sort of near the surface of the Earth, the gravitational field strength becomes uniform. And this is just kind of showing you again from a sort of surface area standpoint how that's the case. Okay, what I want to do is I want to calculate the strength of the gravitational field near the surface of the Earth. And we can do that in this way. Notice Newton's law of universal gravitation says that the force equals capital G. Now let's assume the Earth, I'm going to call it M/E, capital M/E, and the mass of whatever object we have, we're going to call that M2. Okay, and the separation distance between them. Oh, hold on, let me just do something here. Yeah, I knew that was going to happen. Okay, there's some givens that we need here. Notice we have capital G, and I just need to know the mass of the Earth and the radius of the Earth. So the equation we're going to use again is capital G, mass of the Earth, M2 over the distance squared. Okay, now notice if I'm talking about the force on mass 2, right? Well, that's just equal to mass, excuse me, hold on. Let's go in this direction, actually. What I can do here is I can multiply both sides by 1 over mass 2, or divide both sides by mass 2, if you want to think about it that way. Because what I'm trying to figure out is I'm trying to figure out the gravitational field strength, which is kind of looking at what is the force per unit mass exerted on an object at that spot. So notice I get an equation that looks like this. Okay, and if I plug in these numbers, I'm going to plug in 6.67 times 10 to the negative 11th newtons meter squared per coulomb squared. Mass of the Earth, I'm given here as 5.98 times 10 to the 24th kilograms. And the radius of the Earth is 6.37 times 10 to the 6th meters. And that is squared. That's a common thing mistake students make. I'd like you to pause this video, and I'd like you to take a calculator out and actually calculate this. I'm going to give you a few moments to do that. Okay, so when you do this, notice I just did it here, just a little differently. I get 9.8 newtons per kilogram. In other words, a 1 kilogram mass feels a force of 9.8 newtons in Earth's gravitational field near the surface of the Earth. A 2 kilogram mass feels a gravitational force of 19.6 newtons. Now, this should kind of cause a light bulb to go off in your head because we've talked about this before, but just not this way. In fact, last fall, we spent a fair amount of time. You actually did a lab on this where you measured, we didn't call it gravitational field strength, we called it something else. We called it the acceleration due to gravity, okay? But it is another way of thinking about the same thing. So more formally, gravitational field strength is if I take a mass, lowercase m, located a distance r from another mass, capital M, the gravitational field strength is the force per unit mass acting on m. So lowercase g equals capital F over m. Gravitational field strength equals force per unit mass. Okay, the units are newtons per kilogram. And again, I've already asked this, this does sound familiar because it's the weight. It's the weight of an object. But notice another way of thinking about weight, or g, lowercase g in that formula, is thinking that lowercase g is telling you the strength of the gravitational field. In other words, the amount of force per unit mass that an object feels at that point in space because of a very heavy mass that's located already in that region. So on the Earth's surface, the gravitational field strength is calculated pretty exactly to be 9.8 newtons per kilogram, which we know from previous studies, it's 9.8 meters. Another way to think about it is 9.8 meters per second squared. But these are synonymous, and hopefully some light bulbs or some confusions going off in your head. And I'll let you sit with that because I think it's just important, but hopefully you'll start to make a connection between the concepts we've already been studying and this new way of thinking about it. Okay, so the last part, this calculation we just did for the Earth can be generalized for use with any planet or massive body. So if you take a mass m located on the surface of a planet of radius r, we know its weight is F equals m times g, mass times acceleration due to gravity. And we know from universal gravitation, we know that that's true as well. So notice we can set the two equal to each other because it's the same force we're talking about. The lowercase m's cancel out. Notice what happens here. These lowercase m's cancel out, and we get this generalized formula about the gravitational field strength at the surface of a planet that has a mass, capital M, and a radius, capital R. And the same derivation works for any R, right? So it could be a mass that's not located on the surface of the planet. It could be some distance above the surface of the planet. And we would just call that lowercase r, right? A distance r from the center of a planet mass M. So notice these two formulas are very similar. This lower one is the more generalized version that will work in any scenario. This is kind of more specific for objects on the surface of a planet or a star or something. Okay, so I hope you've enjoyed this, and hopefully you have answers to these two essential questions. If not, I recommend you kind of review your notes and maybe go back a little bit. Okay, thank you and have a good rest of your evening.